Okay. Does that look good on your guys' end?
Yep.
Okay. My name is Andrea Haines, and today I will be presenting my capstone project for the Data Science Master's Program. My advisor was Dr. Valova. For this project, I conducted an exploration of long short-term memory networks, also known as LSTMs. The goals of this project were to explore LSTMs using Python, to learn the background and basics of LSTMs, and to implement best models on two natural language processing datasets, one of recipes and one of movie queries. We used two different datasets to see the difference in performance of model types on different datasets. Then finally, I used the trained LSTMs to generate text. Deep learning is an interesting machine learning field involving artificial neural networks, ANNs. These are modeled after biological learning systems and their complex web of connected neurons. The simplest neural network is a perceptron, which takes an input, sums it, applies an activation function, and passes it to an output layer. However, perceptrons are limited to learning functions that are linearly separable. There are many different types of neural networks, and these different types are suited to different tasks. So one type of neural network are recurrent neural networks, or RNNs, which are useful for modeling sequential data, such as time series or natural language. These introduce a recurrent cell, which are useful when context is important or where decisions from previous interactions can influence current ones. Previous hidden states and the input are combined, then go through activation to create a new hidden state or the memory of the network. In RNNs, signals are fed from previous time steps back into the network. However, they're limited in the number of time steps they can look back at due to the signal vanishing or vanishing gradient problem. One solution to this are LSTMs. An LSTM is a type of RNN that adds a memory cell. The memory cell allows for constant error flow during training, and here is a diagram of what that memory cell looks like. The memory cell has a cell state and contains three types of gates: an input gate, a forget gate, and an output gate. These gates learn which data in a sequence is important to keep or throw away, so relevant information continues to be passed through the model. The activation function is applied to all of these gates, and the value determines what is done. Depending on the value, the gates determine when values are allowed to flow in or out of the cell. And then an extension of an LSTM that I explored is a bidirectional LSTM, or BLSTM, which trains two LSTMs, one on the input sequence and then the other on the reverse of the input sequence, and connects to the same output. Another type of RNN that is a solution to the vanishing gradient are gated recurrent units, or GRUs. These are very similar to the LSTMs, but use the hidden state to transfer information and only have two gates. Here is a diagram of a GRU cell. The reset gate decides how much past information to forget, and the update gate decides what information to throw away and what new information to add. GRUs are faster to train than LSTMs, but the winner in performance is case dependent or data dependent. For this project, I used Python and all of these libraries listed on the cell in order to collect and process data, as well as to implement the models. And I conducted my model training using Google Colab, which is a Google product where the user is able to create notebooks and execute Python code through their browser, and it gives you access to virtual machine and GPUs, and that allowed much faster training time than what my laptop was capable of. So for this project, the first data set that I explored was one that I collected, which was a set of 1,038 recipes scraped from allrecipes.com. I found that the URLs from allrecipes.com has a set schema that I was able to generate a random list of numbers and then scrape the recipes found at the URLs. And the fields that I used from the website to build the text of the recipes were the recipe title, the summary of the recipe, nutrition facts, the time and yield of the recipe steps, and the ingredient list. So here is a sample of how the recipes appear on the website and the different fields that I scraped and collected. And then here you can see an example of the compiled full text of one of the recipes in my data set. And then the second data set that we explored was a set of 9,769 movie queries. These were previously split by word and tagged. Since I wasn't looking at the tags, I was looking at text generations, I needed to recombine to create the full text of the queries. So on the left is the original data format, and then on the right is a full text example of one of the movie queries. So for the data to be used in an LSTM, I had to first tokenize the text, which is the first step of natural language processing and involves identifying the basic units that do not need to be decomposed any further. I used NLTK's Natural Language Toolkit's word tokenize to convert each text item into a list of words. And then I also had to pad this list so that everything was the same length. So here you can see what part of a tokenized recipe looks like and how it's separated. And then once this is completed, I vectorize the data or map the words to a numeric representation. This is the format necessary for a neural network's input. And then once this pre-processing was completed, it was time to create the models. The models were built using TensorFlow and Keras APIs. There are 3 ways to create Keras models: sequential, functional API, and model subclassing. The sequential model makes it easy to stack layers in the network, so this is what I chose to explore. And then when you compile the model, you need to select the loss function, the optimizer, and the metrics for the model. I chose categorical cost entropy due to this using the softmax activation function, and because it wasn't a binary problem. I chose the atom optimizer because it is computationally efficient and well suited for problems with large data and large number of parameters. And then finally, the metric that I chose to look at was accuracy, which is the calculation of how often the model's predictions match the labels. The parameters within the models that I investigated to find the best layouts were the number of output dimensions within the embedding layer, which is the size of the vector space, the number of LSTM layers to include in the model, the number of nodes or memory cells within the LSTM layers, and then whether or not to include a dropout layer and what percent dropout to set it as, which is the chance that a neuron will be emitted when training the model. And then finally, the number of dense layers to include. Outside of these parameters, I also tested changing from a unidirectional LSTM to a bidirectional LSTM, and also changing the model type to a GRU. And my parameter selections for my final models were made after 2 epochs of training due to the time involved with training. So on the recipe data, I found that the best model was a BLSTM with 200 output dimension, 300 nodes in BLSTM layer, 2 dense layers, and no dropout layer. I found that training of the recipe models took much longer than the movie model due to the length and complexity of the recipes. And with the movie data, initially I found that the best model was a GRU with 200 output dimensions, a GRU layer, 2 dense layers, and no dropout layer. I found that training of the movie models took roughly a third of the time as the recipe models due to the shorter text entries, even though it was a larger data set. And I also found that GRU training was much faster than LSTM training. And however, after training my initial GRU for 200 epochs, my accuracy seemed to degrade. So I also implemented a movie BLSTM. And I also found that my models overfit on the training data and performed poorly on my testing data. So here is a diagram and a summary of my recipe BLSTM. You can see the embedding layer, the bidirectional layer, and the two dense layers. The movie BLSTM had the same layers, but different output shapes and parameters due to the different data set. And then here is the final model layout of the movie GRU with the embedding layer, GRU layer, and two dense layers. So once my models were compiled, I needed to do training so that the best model weights could be found. Here's what the recipe BLSTM generated for a recipe prior to being trained using a seed word of burger. What you can see from this is that the untrained model's output doesn't necessarily make much sense and it quickly becomes repetitive. I ended up cutting this short. It kept repeating fasten. And then the recipe BLSTM model that was trained for 100 epochs generated this recipe, also using burger as a seed. The trained model's output was closer to what a recipe should look like than what I found with the untrained model, so it did see some improvement. However, they are both lacking in the structure one expects to see in a recipe. There's a lot of repetition of different sections or things that were omitted. The beginning basic layout of a recipe, title, description, and nutrition are produced. The burger, beef, and bean soup 3 is certainly a unique title. I checked all recipes. It does not exist. In fact, burger, beef, and bean soup 1 and 2 also don't exist. And I would not recommend attempting this recipe. We're missing an ingredient list, and it's very scrambled as far as instructions go. There's a lack of cohesion needed in a recipe. And then here are my results from the movie GRU with the untrained example and then the trained output. The GRU final output seems like a reasonable query in terms of its structure. And then finally, I have the output from the movie BLSTM. Like the recipe untrained model's results, repetition was problem with the one before it was trained. However, the final output after training seems reasonable and makes sense, and it was not a replication from the data set. Are there any questions?
I will echo this request. Any questions from the audience, please? Or the panelists?
May I ask a question?
Of
Sure.
course, go ahead.
Sure. I'm a bit of a novice, so sorry if this is a silly question. I'd like to understand your structure of your LSTM and your GRU. In particular, it's not exactly clear to me how the gate performs. Is it such that you have a neuron and that neuron has an activation function with input, and then it's either going to fire or not, and that's going to determine which gate it goes through, or is it that the gate has its own related function, and that'll determine whether the information gets passed or not? So is the gate a consequence of the neuron, or is the gate its own independent calculation?
I believe it's a type of neuron, if that's correct. So it has its activation functions, and then so here you can see these functions, and then that determines what the gate does based on which type of gate it is.
If I may offer supplement to this answer, I suppose that in the last years of machine learning, we have moved away from the simpler neuron definition from the past. So I would refer to these as units that do have activation function. So it's a little bit, sorry, that's running out of time. But anyway, it's a bit more elevated concept, I guess one would say, to the traditional neuron.
All right,
Any
awesome.
other
Thank you.
Thank you.
any other questions, please? Maybe the panelists have one last question as we're out of time.
Leslie, did you have any, or do you want me to go?
I'm good. I don't have any questions.
Okay. So just, I guess, quick question. It looked like you explored many different architecture configurations. Was this kind of like a random search for good ones, or were you guided by some previous experience of how the architectures should be designed? And then also just kind of curious, like, what were the runtimes for this, and did you have to use GPUs or anything like that?
So this was kind of I kind of increased the different, let me go back to the different layers and the different things. I did look at papers to see kind of what's commonly said. I mean, you would expect that with some of these, the more complex, the better results you would expect, but then it's so data dependent. So it was kind of just seeing and comparing if I ended up with different models for the two data sets, and just how that affected performance. So just an overall exploration of what worked best based on the data. And then I know there was a second part to that question, but I've already forgotten what that was.
Any specialized hardware needed to solve these problems, like GPUs or multiple GPUs?
So when so the first time that I attempted to train my recipe LSTM, it took days. But then when I was able to use the Google Colab, it was so much faster. It was more like 12 hours for the 100 training epochs. But then I was also limited because it kind of assigns you the GPU or the machine, and then it's based off of demand. So you might have a faster one, you might not. So I ended up having to like save off my models because it's connected to Google Drive, and then pick up training again based off of what was allocated to me in terms of resources. So that was definitely an interesting experience.
All right, great. Thanks so much for the talk. Thank you.
Thank you.
Thank you, Andrea. So we're running behind, but